We're now going to begin talking about our next specific force, which is friction, but it's going to be a different type of friction. So what we've been dealing with so far has been kinetic friction, okay? And that's the friction when objects are sliding. Now, I do want to make that a really important point. It's when objects are sliding along the ground. So kinetic normally means moving, but just because an object's moving doesn't mean we're dealing with kinetic friction. It has to specifically be sliding. Okay, there's another type of friction though, and that is static friction. And that exists when objects are not sliding across a surface. There are two quick examples I can think of. One would be if you have a really, really heavy box and you're trying to push that box, and you push with all your might, but you're unable to move the box. That would be a case where static friction is coming into play, and that's the force that's actually preventing you from moving that box. You exert a force this way, static friction between the box and the floor pushes back, and ultimately you're unable to move the box. So that's the first case. Static friction, though, also can exist when objects are moving but not sliding relative to the surface. So maybe you have a tray of drinks, all right, and as you're walking through the restaurant or something, those drinks are staying on that tray. They're not sliding on that tray. The force keeping them from sliding when you turn or when you speed up or slow down to get to the table, that's static friction. It also comes into play a lot with cars, okay, and the tires, all right? Most of the time, static friction is the force that exists between your tires and the road. The only exception is if you're skidding or sliding, which obviously is not something that you want to be doing. But in most cases, when your tires are not skidding or sliding, they're just rolling along the road, the force you're dealing with is static friction. So it actually does come into play quite often. A few key changes here with static friction. Instead of talking about mu k, the coefficient of kinetic friction, we're talking about mu s. And those numbers will be different numbers. All right. The one thing that we do know is that mu k will always be less than or equal to mu s. So the coefficient of kinetic friction will always be less than or equal to the coefficient of static friction. Another thing that's important is directionally. So kinetic friction was easy. Kinetic friction always opposed the direction of the velocity when an object was sliding across a surface. It went in the opposite direction. Static friction opposes the direction the object wants to move. Okay, so we're oftentimes going to think about what way would this object move if there were no friction, and static friction is going to be the opposite of that. All right. As you'll see on the next slide, calculating it can be a little bit trickier than kinetic. Before we jump into the formula here, I want to talk about this graph that we have over here because this is a really important graph. And so let's talk about this situation we have in this graph. So this graph is for a box that's sitting at rest on some surface, and we're pushing it with some force. They're calling that FA, the applied force. Okay, and we slowly increase how much force we apply to this box, how much we're pushing with. But initially, the box doesn't move, and the reason it doesn't move is because we have a frictional force. And in this case, it is a static frictional force, and it's opposing the direction the object wants to move. We're pushing the box to the right. That box wants to move to the right, but friction prevents it from doing so. And that kind of goes back to what we were talking about on the last slide, how friction opposes the direction the object wants to move. Let's think about our F equals ma here in the x direction. So the forces we're going to have the applied force minus the force of friction, and that's going to be equal to max. Okay, so let's take a look at this graph now. Here's what we're seeing. We see that we slowly are increasing our applied force, pushing with more and more force. What ends up happening is that friction is increasing at the same rate. So when we push with 10 newtons of force, friction is 10. When we push with 20, friction is 20. When we push with 30, friction is 30. And think about what that means in terms of our F equals ma. These two forces are equal, so we're going to have a situation where we're not accelerating. So that's what we're seeing at first in this situation. This object is at rest, and it remains at rest because our frictional force matches our applied force. okay, that frictional force starts out with zero force when we're barely applying any force, and that frictional force slowly increases at the same rate that our applied force increases, always canceling out that applied force and keeping the object at rest. All right, so that's what we're seeing for this section of the graph. And this brings up something really important, something that's different with static friction than with kinetic friction. And that is that static friction can vary. Okay, static friction is not one constant number. There is a range that static friction can have. All right, and that range will depend on how much force we need to keep the object at rest. There eventually, though, is a breaking point. Okay, and that happens right here. And what we see here, and we do use this term, we say we break static friction at this point. So, up until that point, we were pulling progressively harder and harder. Static friction was matching us. We pull with 10, it matches us. We pull with 30, it matches us. We get right here to about 40 newtons, all right? What ends up happening is static friction no longer can produce enough force to keep the object at rest. And so, all right, the object begins to move, and what we see here is that the friction drops down and hovers around a steady rate here. And that steady rate is our kinetic friction. Okay, so static friction is increasing, increasing, increasing to match that applied force until we break static friction. All of a sudden, we're in a kinetic friction case, and it remains relatively constant. So that leads us into what the formula looks like for the force of friction. And the formula is that the force of friction, when we're talking about static, is less than or equal to mu s, our coefficient of friction, times the normal force. So, two things change compared to our kinetic. Number one, we have this less than or equal to sign. And number two, we're now dealing with the static coefficient as opposed to the kinetic coefficient. And the reason for this less than or equal to is what we're seeing in this graph. Okay? When we calculate the force of static friction, we're calculating the maximum possible force. All right, the most that it can exert before the object starts to slide. However, it could be less than that amount depending on how much friction we need to keep the object from sliding. So we just have a chart here comparing the two, just hitting on some of the main differences. Number one, for kinetic, object is sliding, whereas for static, it's not sliding, but it may be moving, and we'll look at some more examples of that later on. We have our two different formula. Again, coefficient of friction changes, whether we're talking about static or kinetic, and we have an equals for kinetic. All right, we know how much kinetic friction is. Once it starts sliding, that's a set amount, but static is not. We can only find the maximum. Talked about directionally, kinetic opposes the direction of the object's moving or sliding. Static opposes the direction the object wants to move. Right, and then the biggest thing, and this really comes from the formula, we have a constant magnitude for kinetic, but static gives us the maximum possible force instead of what the actual force will be. A few tips for doing these. Kinetic friction, as I said before, doesn't really have any tricks, but that less than or equals to really makes things a little bit more difficult. And the easiest way, and I know I've said this like 5 times already, but the easiest way I can think about this is when you do mu times the normal force, it gives you the maximum force of friction. Do not assume friction is at a maximum unless there's something in the problem that indicates to you that it will be. All right? So go ahead and find that maximum, but don't assume that that's what the actual force of friction will be unless something in the problem indicates to you that it is. Now, if it's not at a maximum, you might be thinking, how are we going to figure out what that force is? You're simply going to determine that from the free body diagram and your F equals ma equation. You can always use your F equals ma to find the force of friction. What you can't always do is assume that that force of friction is equal to mu times the normal force. Okay, so we have a practice problem here. We have a 19 kilogram cardboard box sitting on a floor. We're given both the coefficient of kinetic and static friction, and we want to know how much force is needed to make the box begin to move, and if this force is maintained, what will the acceleration be? So of course, just like any other force problem, we're going to start with our free body diagram and setting up our F equals ma. So we have our normal force going up, force of gravity going down. It says we're pushing with a horizontal force, So I'm going to say there's an FP going like that horizontally, all right? And we have a force of friction, all right? In both cases, when we are getting the box moving, we have static friction, and when we are keeping it in motion, we have kinetic. I'm going to start by setting up my MA here. Sum of the forces in the y equals MAY. So we have Fn minus Fg equals m times my y acceleration. In both the static and kinetic cases, that y acceleration is going to be 0 because we're not accelerating vertically here. So I can sub in for my force of gravity. So Fn minus 19 times 9.8, just mg there, equals 0. And so my normal force here is going to be equal to 186.2 newtons. And that's the same, like I said, for both the static or the kinetic cases. So let's take a look at the static case now and look at our forces in the x direction. So sum of the forces in the x is equal to max. We have Fp minus Ff is equal to m times my x acceleration. All right, so there's a really, really important phrase in this problem, and it means a lot of things. And that phrase is, what does the minimum force need to get the box moving? Two things that means. Number one, it means that Ff is at a maximum. So if we're thinking about that point where we exert enough force to make the box begin to move, our force of friction is at a maximum. Number two, if we're exerting just enough, that minimum force to make it move, our acceleration at that point when we break static friction will be 0. Obviously, once it goes into motion and we switch to kinetic friction, we may have an acceleration, but at that point where we break static friction, our acceleration is going to be 0. So going back to our F equals ma, that means two things. All right. Number one, that means here we can substitute in μs times our normal force. All right. That less than or equals to becomes just an equals to when we know that we're at a maximum force, and we've just justified that we are at a maximum force. Number two, this left side, or that right side, goes away and becomes 0. So we can say that Fp is equal to μs, which is 0.35, times our normal force, which is 186.2, and we end up getting a pushing force, a minimum pushing force to make it begin to move, of 65.17 newtons. All right, moving on to our kinetic case here. All right, we're going to set up our F equals ma once again, and we know that that force, that pushing force, is maintained, and we want to find out what the acceleration is now. So our F equals ma is going to look exactly the same. Fp minus Ff equals max. We know that pushing force is this 65.17 that we just solved for. Since we're dealing with kinetic friction, we can just sub in uk times our normal force. We know that kinetic is always equal to that. And here we actually have an acceleration, so we can't just cross off that right side. So 65.17 minus our coefficient of kinetic friction, 0.29, times our normal force, 186.2. And that's going to be equal to 19ax. So we end up getting 11.17 equals 19ax. So that means that x acceleration is 0.588 meters per second squared. Moving on to this last practice problem here, and I think this is one that really does a nice job of illustrating the nature of static friction. So we have a 60 kilogram object at rest on a level floor. We know the coefficient of kinetic and static friction between the floor and the box, and we want to find what the force of friction is in a few different situations. So we're going to start once again with our free body diagram. Actually looks exactly the same as the last problem. Pushing force to the right, normal going up, gravity going down, and our force of friction going to the left. And I'm going to set up once again the sum of the forces in the y direction. Okay, so we're going to have the normal force and the force of gravity are going to be our two forces. So Fn minus Fg, and that's going to be equal to 0 because we're not accelerating vertically once again. So Fn minus 60 times 9.8 equals 0, which means that our normal force here is 588 newtons. I'm also going to set up the sum of the forces in the x direction here, okay, because that's what we always do. So we have FP minus FF equals MAX. Now, before I move on, I'm going to take a look at what this problem is actually asking. It's saying, what is the force of friction? That's what we're trying to find here. So a question that I'd be asking myself right now is, if we're trying to find the force of friction, are we dealing with a static case or are we dealing with a kinetic case? And this might seem a little bit backwards, but what I'm actually going to do is I'm going to calculate both the static friction, the maximum static friction, and the kinetic. So I know that my static friction is going to be less than or equal to mu s times my normal force. So my force of friction for static is going to be less than or equal to 0.45 times that 588. And so that means the force of friction, the maximum force of friction for static friction, is 264.6 newtons. Okay, and for kinetic, same basic setup, except we don't have that less than or equals to. That force of friction is just mu k times my normal, so it's going to be 0.35 times 588, and I end up getting a kinetic frictional force of 205.8 newtons. So, back to the question at hand. If I push with a horizontal force of 200 newtons, okay, keeping in mind that the object is initially at rest, what will the frictional force be? Well, I see that that 200 is less than that maximum force of static friction. It's not enough to break static friction. And so what that means is this object is staying at rest. So what I can say is 200 minus FF is equal to 0. And so my force of friction is simply 200 newtons. That 200 is not enough to make this object begin to move. Okay? It's also not the maximum static friction. All right? Friction can be up to 264.6 newtons, but in this case, we only need 200 to keep the object at rest, and so that's how much friction is going to push with 200 newtons of force backwards, opposing that pushing force to keep this object at rest. Moving on to part B, we're now pushing with 250 newtons of force. Once again, that's not enough to get the object moving if it's initially at rest, because static friction can be up to 264.6 newtons. So we still will be keeping that object at rest. I would note that if the object was already in motion, it would be enough to exceed kinetic friction and keep it moving permanently. All right, but it's not enough to make it begin to move. And so I'm back to my F equals ma to find the force of friction. So I'm going to say Fp minus Ff equals 0, because I know it's not actually going to start moving in this case. 250 minus Ff equals 0, so my force of friction just matches that pushing force, 250 newtons of force. We move on to part C. If we have a horizontal pushing force of 300 newtons, what is my force of friction? Well, now, all right, don't get tempted to say that force of friction is going to be 300, because my maximum is 264.6. So if I push with 300 newtons of force, this object will begin moving, and that means my force of friction is just my kinetic friction, 205.8 newtons.